Can you see my screen? Parker.
Yes, I can see it.
Good. All right, let's start. Maybe others will join us later. Anyway, it's gonna be recorded. Let me ask you if you had a chance to start working on this, and maybe something already have done.
I haven't had a chance to start working on it. I've looked over it and kind of read through it, trying to figure out how to start on it. Um, but basically, all we're doing is doing the alphabetic keyboard for 4 inputs, or
Mm-hmm.
well, it'd be 10 separate inputs. But
The key point in this assignment is to learn how to deal with the memory, because without the memory, a computer is non-existent because you cannot just pretend to process the data. You have to store the results. And in any modern computer, actually in any classical computer even more, memory is the uh, crucial part. So a result of calculation has to be stored somewhere, and as you probably know, there are different levels of memory existing in computer system. So the memory that we are currently working with in this assignment is uh, it's actually not the memory that you purchase to purchase to install in your computer, like those like 4 gigs, 8 gigabytes, 16 gigabyte, but more like a memory that is present in a CPU itself. Usually, this kind of memory is considered, is called CPU registers. And it is very limited, it is very fast, but this memory is what has been used for uh, arithmetical and logical operations performed by the processor. So anytime a processor needs to add numbers or multiply numbers or do some other operation, it doesn't need to read data. It not always needs to read data from the main memory, but it likely can find something on its registers. Of course, if the data is not in the register, it has to be loaded first into the register, and then it performs the operation and updates the main memory. So what we do here, even though it pretends to deal with the keyboard, but you probably can think of this assignment as a mini computer on a chip. So we do have some input output, we do have memory, we do have some processing, and pretty much if you look at this functionality as from the perspective of a big picture, this is a computer. So uh, today, for the tutorial purposes, I'm going to consider a simplified problem uh, very much alike to this assignment, but instead of, so we will reduce number of inputs, we will reduce capacity of the memory, we will reduce combinations that are supported, number of states, etc., etc. But anyway, what we will develop today probably can be used as the foundation to implement your own uh, your own implementation of that keyboard controller. So the problem for us to solve today will be, let me just write this down, problem. So we will have, okay, let me say 3 inputs. We will have certain number of states that I'm not clear to identify right now, and our outputs will be pretty much generated by analogy to the problem definition in the assignment statement. So those 3 inputs, let me just call them uh, keyboard keys A, B, and C. We're not going to have the control, we're not going to extend that far, but out of these three keys, we can introduce the following scenarios. A single press of a key, and it could be either A, press and release, B, press and release, C, press and release. We can also introduce sequences like this. We're going to consider only two sequences by analogy to the assignment. The sequence here doesn't mean that we press A and while holding it press B. So A-B sequence means that we press and release A and then press and release B, and we don't care what will be pressed next. As long as A, B have been pressed in sequence, we have to do something separate about this sequence. And let us introduce a couple of the parallel presses. So we will have A plus B press and A plus C press. So which means that two buttons can be pressed at the same time. In this case, A plus B and A plus C. And here it is not important which one was pressed before, either A or B, but what is important, as long as A is being pressed, or as long as we hold A, then B is pressed, and then both are released, and we actually don't control in what sequence they are released. So, but the two buttons at some point in time have to be pressed simultaneously. So these are our inputs, and let us try to estimate number of states to implement these inputs. First of all, we will have to have something called initialization state. From this initialization state to this initialization state, our system should go when the power is applied to the system. So this will be initial state of our memory. And then we want to make sure that we introduce sufficient number of states to differentiate desired behavior. Desired behavior in our case would be to implement something called Moore automata. It simply means that our outputs depend on current state only. So from the perspective of implementation, Moore automata or finite state machine will introduce change of the output with no respect to how inputs are changed. Change of input will in turn result in the change of the state, but output will be changed only when the state is changed. The big difference between the two types of finite state machine, Moore and Mealy, is that usually Mealy finite state machine, the one that allows output to be changed not only with respect to the state but also with respect to the input, it requires usually less number of states, because we can keep the same state and change the output when the input gets changed. If you think of a keyboard that doesn't require sophisticated combinations, but let us say only requires single presses, like in our first case, A, either A only or B only or C only, we could simply introduce a single state of this finite state machine that will be called something like single key press. As long as finite state machine is in that state, any corresponding input will be either A or B or C, will trigger a particular output. So this would be the case of the Mealy finite state machine, that one same state can serve output update just with respect to the input change. The Moore finite state machine, the one that we are considering right now, we'll assume that for every combination here we have to introduce our own state, and the finite state machine will go to that particular state upon change of input condition. Let us try to identify those states. We clearly want to produce the following output, because usually from the perspective of input to output mapping, we can think about states. So our output will be a single press A, a single press B, a single press C, a sequence AB, sequence AC, and parallel press AB, parallel press AC. So on top of the initialization state, we have to introduce at least 5, 6, 7 additional states that will correspond to particular output. So you may think of our output to be something with the 7 output. Something wrong with my pen. Okay, I probably don't need to write in this area. So there are 7 outputs, and we want to have those 7 states that will result in activating of the output as long as finite state machine in that particular state. So let me introduce the 7 states. 1, 2, 3, 4, 5, 6, 7 that are defined on top of the initialization state. And those 7 states will match the 7 outputs. So when our finite state machine is in state A, for example, A plus B, A plus C. Okay, when our finite state machine is in state A, the first output A will be activated. When our finite state machine is in state B, the second output will be activated. So these 7 outputs can actually be directly mapped to the 7 described states. Now, important part is how do we change the state in our finite state machine. We know that originally we are in the initialization state over here. This is our state when the power is just applied. But then we want to react to particular presses of the input buttons. And let me just say that from the init state, any one of these inputs can be generated. So now we're talking about 1, 2, 3, 4, 5, 6, 7 different input signals that are possible in our finite state machine. So when, for example, input A arrives, our finite state machine goes from initialization to input A. And we know that state A is mapped to output A, so an LED indicator will be activated when we move into the state A. Now, we do have only 7 states, but pretty much what you always have to have in mind that having 7 inputs and 7 states, we are now talking about tremendous number of combinations, assuming that from state A there could be input A, there could be input B, there could be input C, there could be input AB, AC, A plus B, A plus C, etc., etc. And then if, for example, we move on from A to state B, while being in state B, there also could be input A, B, C, D. So pretty much our transition map in this case would assume that from any given state we can move to any given other state, and that would create a total mess in our diagram. And this is only for the three buttons. The modern keyboard of a DOS desktop computer, probably, if I'm not mistaken, uh, includes more than 100 keyboard keys. So in this case, the finite state machine would be overcomplicated. So from this perspective, we probably want to do something to actually not to introduce the A plus B state or A plus C or sequence A, B, and AC as a direct reaction to happen when some special input is engaged. Because our input encoder will never be able to tell us that it is the input A followed by B. Because for the sequence to be detected, we really have to memorize the fact that A was pressed before and then B was pressed after. And the memorization is actually the purpose of the finite state machine. So, in other words, sequence AB cannot be detected on the input side. Sequence AB can only be detected within the finite state machine. And that sequence will result in the transition to state. So let me just illustrate this concept. When from initialization state we move on to state A by means of signal A. Now, if signal B is given, which means a single key with the label B has been pressed, we move on not to a single state B, but we move on to the state A followed by B, the sequence AB, because we know that just before arriving here, we have been in state A, and this is the guarantee that input A was followed by input B. So from A, we move on to B. And now from input, from the state AB, we actually need to do something to be ready to receive other inputs. And it would be very inconvenient to actually assume each of these states from the perspective of mimicking functionality of the initialization state. In other words, when we are in state AB, we should be able to expect any one of these three inputs, either A or B or C. And we have to react in the same way as we would react if we've been at state initialization. So we don't want to duplicate the logic, and in this case, our next transition that is very important is transit from AB back to initialization when the sequence when some special command is received. That special command can be considered as, for example, release of a key, or let me just call this no key. No, it's not the key. Let me just call this N. N will mean nothing. Nothing is pressed. So once we move to sequence to state AB, when nothing is pressed means after we release key of B, we are our input keyboard in the state that no key is pressed. When no key is pressed, we will move on to initialization state. Okay? What will happen if no key is pressed when we are in the initialization state? We probably want to go back to the initialization state. What will happen if n input is received when we are in the A state, we go back to the initialization. All right. So in this case, when we are in the state A, and by the way, this could be incorrect transition because we don't want to go back to initialization once we are in state A, because it would not allow us to move on to B, because we know that a press of the key is immediately followed by the release of the key. If release of the key will bring us to the initialization state, then we have no chance to follow in this direction. So let me just say this. Release of key A doesn't make any change if we were in state A. That actually illustrates the necessity to introduce additional state. That additional state will be, I would say, will be called A prime. I call this A prime, and it is different state from A, because when we are in state A, let me make another correction here. When we are in state A, we want to consider A being nothing more but a standalone key press. Standalone key press, it means that now we can recover the no key signal or release of A. In other words, that state is not involved in the sequence combination into A-B state transition. I probably want to move that A prime thing somewhere here. A prime. So we go into A prime state technically also from the initialization. But from initialization, we also want it to be from this transition also should take place when the key of A is pressed. And this is the contradiction. Same input cannot result in the transition of the finite state machine to both states, because a finite state machine can be in a single state, when can only be in a single state. It cannot be at both states at the same time. So in other words, we cannot authorize that link. But we still need that additional state. Probably we need this additional state, because it will be source to the transition into AB. So from state A prime, having the signal B, input signal B received, we will transit to AB, and then upon release of B, we will go to the initialization state. Now, how can we enter the state A prime? We can probably enter state A prime if that is actually tricky. If you think of in what way state A and state A prime are different, they are different from, at least from one standpoint, by considering the fact that from state A, one of the outputs will be engaged. From state A prime, output will not be engaged. In other words, state A is associated with a standalone press of A, key A, and then going back to initialization. State A prime is just an intermediate state before the intermediate state along the way from the initialization to the state AB. And if you try to think in terms of how a state A prime can be assigned, excuse me, state A prime can be assigned from the state A. And this would happen if some delay is present. So now let me just, that logic is still not final, but at least it introduces some important signal called delay. Delay, it's not something that we can produce in our keyboard. Actually, we do produce it on the keyboard, but it is also a measure of, it has the nature of a human being to introduce the intent either to press single A or single A followed by B. We usually, if you try to analyze your habits when you type in on the keyboard, you're not that much interested in sequences A, B, or I, C and consider them to be commands. Because usually these sequences are processed not on the low level as we do here, but on the level of the operating system or on the level of the software that is running on the operating system. From this perspective, the difference between state A and state A prime would be to assume that a sequence AB can be generated when we pressed A, immediately released A, and immediately pressed B. So in other words, delay between release of A and press of B is actually small enough. But if we press character A and then release character A, and within certain amount of time we did not press character B, then signal A would be considered as a standalone signal A, and we have to go back to initialization state. So that actually makes our state diagram being rendered in correct fashion. And let me try to wipe it off, because we want now to redesign it from the perspective of having a delay. And at the very beginning, I'm not going to introduce other states, but I want to finish A and AB separation, and then you will see that other states can actually be introduced in a very similar manner. So we still need state A, and we go to this state A by means of signal A. Now, from this standpoint, we're talking about a delay that will be either introduced or will not be introduced. So if a delay is introduced, delay here, it's actually delay after releasing of the releasing of A. So in other words, from A, we first of all activate signal N, which is nothing. So in other words, we release character A. And then this state could be state W, which is wait. In state W, we can initialize a timer or some form of delay counting mechanism. And that delay counting mechanism will tell us that before the timer expired, signal B was introduced, or signal B was not introduced and the timer got expired. So in this case, when we are in the waiting state, we're now talking about another signal. Not here, but wait, this is not a state. Timer. Timer is the signal. W is the state, timer is the signal. So, and timer will be considered from the standpoint of expiration. Expired. Timer expired. So, when timer expired, while being in W state, signal T will be generated, and we go back to the initialization state. Now, if timer is not expired, then we want to think about pressing of a signal B. Signal B will move on us to state AB. And when we are in state B, AB, we generate some output. And now we actually want to release key of B, and then move on to back to the initialization state. So let us think of what will happen if we are in the waiting state, and we actually are waiting for the B to be pressed, but we are waiting too long. So if, for example, our timer expiration period is set to, I don't know, 500 milliseconds. 500 milliseconds, that's half of a second, and the timer will be expired very frequently. Frequently to distinct our intent to press single A or a sequence AB. So if the timer is expired, we go back to the initialization. We know that at this time, since the N input has been received previously, key A is no longer pressed, and we are actually in the initialization state. Now, if the timer has not expired and character B is pressed, we move on to state AB and we generate the output. If B is not there, eventually the timer will expire. So in state W, we actually do have two mutually exclusive outcomes, and either one or the second one will be activated. So you can think of what will happen if B is not pressed, then the timer will expire. If B is pressed, we move on to here. From the same perspective, from state W, we can introduce state AC, but in this case, input C will be required. And when nothing is pressed, we move on back to the initialization state. Okay? And let me just mark our state with the asterisk sign if that state requires some output. So state A requires output, state AB requires output, state AC requires output. Now, we dealt with single A, AB, and AC. The single B and single C are pretty straightforward, and we don't really need to introduce the W state to handle them, because as long as we go into state B by means of signal B, we can go back to initialization state as soon as the B is no longer pressed. And same with the C. Okay, let me draw a C here. So this will be C signal, and the back route will be guaranteed by signal N. So we don't need C in this part. Okay, so now we addressed single A, single B, single C, sequence AB, sequence AC. What should we do when we want to deal with A and B being pressed at the same time? It means that when A is pressed, we don't want the release condition to take place. So from A, we want to allow character B to be pressed. So in other words, from A, since we want A and B and A and C, we probably want to draw two arrows. And I will develop them at the same time. So when we are in state A, but the key A has not been released, not yet, because if it is released, we go to the waiting state. If it is not released, then it is possible that either B or C signal have been sent. So A followed by B, and then from this state, let me call it A plus B, A plus C. When we are in this state, it means both A and B are pressed. And since we don't really care about sequence in which the two keys are released, we can just say that from these two states, we only care about signal N. And signal N will bring us back to the initialization. So, for example, we are in state AB, A plus B. And let us say A has been released, we're still in the state A plus B. And then B has been released. And in this case, signal N is generated and we go to the initialization. If B released first, we don't go anywhere before A is released. When A is released, now it is the signal N, and we go to the initialization. And since both A plus B and A plus C could also start not only from A, but could also start from B or from C respectively, then we can introduce from B to here if A is pressed. So B first and then A, and we go to A plus B. If B first followed by total release, we go to the initialization. But if instead B, A is received, we go to A plus B. And same here, from C, if A received, we go to A plus C. Okay? So pretty much that is our diagram, our state diagram. Our state diagram shows the transition of states that will be made with respect to particular input signals. And by asterisk, I'm going to mark B, C, because those states will engage certain outputs. And since we have 7 outputs, I'm going to have 7 states marked with the asterisk. 1, 2, 3, 4, 5, 6, 7. Okay? So that is our diagram. Let me try to save it. Hope it's possible. Probably here. Now that's to log in. Maybe here. Download image. Okay. At least we have now our diagram handy. So let us now introduce the more quantitative vision to our state diagram. And I will clean up this part of my drawing. All right. And we'll continue drawing here. So how many states do we have? Initialization, A, B, and C stand alone. State W, A plus B, A plus C, A, B, A, C. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 states. 9 states requires 4 bits of data. 4 bits of the storage to memorize the state. I know this because if you calculate logarithm of 9 base 2 and perform the flow operation, you will get number you will get number 3. We want to round it up. So in other words, 2 raised to the power of 3, it is just 8, and it is less than required 9 states. So we cannot use 3 bits. But 2 raised to the power of 4 is 16, and it is greater or equal than 9. So we can use the 4 bits. Right? So 4 bits of data we have to introduce into our memory. It means that there will be 4 dedicated triggers. Let us now talk about inputs. How many different inputs we have? We have input A, we have input N, B, C, and the timer. The timer is something that can get expired, but usually timer needs to be also started. So in this case, the timer can be considered as supplementary equipment, but that supplementary equipment needs to be um, activated, not always, but only at particular times. We actually want to activate the timer as soon as we entered state W. Once we entered state W, we want to start the timer, and in other words, our output can be considered as having one additional output to start the timer. So we want to mark state W with the asterisk character to actually introduce additional output that will be start of the timer. And timer will be started, and once it is expired, then it will generate the signal that will come in. So timer is a signal, input signal, but it is not a signal generated by our keyboard. Pretty much from our keyboard we have the 1, 2, 3 inputs that come directly from the keyboard buttons, and each one of them is considered to be implemented as a switch, and a switch can be either open or closed. If all three switches are open, it is the signal N. If, for example, switch A is closed by B and C are open, it is signal A. When B is closed, A and C are open, it is B, etc., etc. When A and B are closed at the same time, we don't consider this to be a signal, because the only sense simultaneous closing of these two keys will make sense, the only sense it will make, when we translate, when we are present in one state and translate to another state. So in other words, we don't want to consider input from A and B being pressed at the same time. We only consider A only, or B only, or C only, or nothing. And we also have the signal from the timer. This is that signal. So pretty much we do have 4 inputs and our input encoder. Our input encoder will generate A, B, and C, will generate N, will generate T. And you probably can ask, why do we need some form of input encoder if we already have 4 signals on the input side with the same names as the 4 output on the output side? The reason that we need input encoder, because at some point we want to prevent combinations like A and B being pressed at the same time. Just think about possibility which is which tends to 0, that A and B are in fact pressed at the same time. Not A immediately followed by B, not B immediately followed by A, but A and B pressed at the same time. From the perspective of implementation, same time is the interval, which is very short, and it is less than the time required for the transition from initialization to A. Let us just say that A has been pressed just a moment before the B. So we go to A, and then we receive signal B, and we come here. So it is not A and B, A followed by B, while A is pressed, but it is A and B at the same time. We don't have signal AB here. We only have A and B. That's why we have to clearly separate the logic. If A and B will be pressed at the same time, then none of these outputs will be activated. Okay? So we have 4 inputs and 5 outputs of our input encoder. And let us try to draw the state, not the state diagram, but the truth table for the encoder. And I have to clean these things up. And let me draw the table. So in my table, I will clearly have the separation between the input side and the output side. I do have 4 inputs, A, B, C. Okay, probably I have a bit more space here. A, B, C, and the timer. And my outputs are A, B, C, timer, and N. The 4 inputs must be associated with all possible combinations. There are 16 combinations. We don't use the gray code, just straightforward binary encoding of the sequence. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let me break them in groups of 4 for convenience. And now let us try to design our input encoder so it will respond to the needs of how our signals have to be introduced. So let us just say neither A or B or C is pressed and the timer expiration is not there. Timer has not expired yet. That is clearly indication of N. Okay. Now, when the timer got expired and like this, and neither A or B or C is pressed, what kind of signal is this? Clearly that we don't want to generate, we actually can generate T, but let us just think whether or not we have to place 1 in this position. So it is complete release of all switches A, B, and C, and timer got expired. In the state W, we are actually facing the situation when none of the keys is pressed, and then the timer get expired. So that is the situation when the timer output of the input encoder has to be activated. But this, do we need to uh, enable the output N? Probably not, because once we are in state W, we no longer want to receive an N. But for the sake of optimization, we actually can generate N because it is harmless. The more ones we have in any one of these columns, the easier will be to optimize those functions. So having one in column N in this case, this one doesn't change anything from the perspective of the logic, because having 1 or 0 in this position makes no difference, because timer is expired in state when none of the inputs is present, will result in changing to this state. What is important, we will not have we don't have any trace from state W, any outcome from state W with signal N. Signal N is used only to enter to state W, never to escape it. That's why, okay, let me just make the clearest assignments first and then we'll do the rest. Let us just say that N is undefined here. We don't know how to assign it. Now, when C only is pressed, it is the clear indication that C will be there. When C and timer expired, we cannot say that this signal will be engaged, because we're supposed to stay in this state and wait for either C or the timer, whichever comes first. They cannot come at the same time. If they come at the same time, it is a mistake. Okay, so we don't mark the timer expiration here because it is the prohibited combination, 1 and 1 in both of these positions. Now B is active, and then B and the timer also prohibited combination. Then B and C is a prohibited combination. We don't want B and C pressed at the same time. And BC timer is a prohibited combination. Okay. Now A only is good. A and timer. A and timer can actually be utilized to follow this direction, because we don't have any outcome with A and timer. So in other words, at the moment when timer gets expired, we don't mind for character A to be pressed at exact same moment. But it is pretty much the same situation as having timer being combined with signal none. We do know that it will take place, but we don't count for the none here. That's why in this situation we don't count for none. Now A and C we don't mark, A, C timer we don't mark, A, B we don't mark, and pretty much the rest is just the combination of all others. So at least we have we do have ones in each and every column. It means that our truth table can be implemented. We can actually say that in those lines that are marked with ones, other signals should be set to 0. Actually, they are not required to be set to 0. But if we do so, then we can clearly state that these combinations have only a single way to be generated. So in other words, signal N is only engaged at the time when none of the keys is pressed and the timer is not expired. Timer will be not expired when it will not be started. And it actually depends on the implementation of the timer, because timer expiration bit can be considered permanent when timer is expired and it will stay in the expired state. So in other words, once we follow this route and the timer got expired, the timer remains expired, and in this case t will be 1. It will actually help us for the optimization purpose, and we actually can make this assumption. So when timer is expired and it constantly outputs the value of 1 with signal t, then it is not just A. So that signal A is from the right side, but that signal A can be generated with no respect to the current value of t. So in other words, for the optimization purposes, we can say that A only can be combined with A and the timer expired. We cannot do the same with B and the timer, C and the timer, because from the W state we have to clearly separate either B or C or timer. They cannot be combined from the W state. But A is not used with the W state. That's why we can activate A either with expired timer or without expired timer. These two bits will both work for us. Now, where else the expired timer can be useful? Probably here, because expired timer can be generated when no key is pressed. So no key is pressed and it is expired. And by the way, it probably can be generated, can be marked here. No, we don't want this. Let me say this. The diagram in its current state is functionable because, as I said, the necessary condition here is to have 1 in at least one column. Theoretically, you can actually replace that 0 by 1, and it will slightly help you to optimize your input encoder. But change this 1, you have to clearly understand why in this position 0 or 1 is not important. Because if you have 0 in this position, you do not generate none when timer is expired. So timer is expired, and in the initialization state with the expired timer, we will not have n output or n output of the input encoder be applied. So in other words, timer remains expired, once we moved here. And actually that one is really needed here, because if we don't do this with the expired timer, we will not be able to handle this n or any one of these n's, because the timer will be expired. As soon as we went along this path, the timer remains expired. So n has to be combined with the expired timer always, and that's why we put 1 in this position. So C and T can be used at the same time, B and T cannot be used at the same time, B and C cannot be used at the same time. So pretty much we and A and T can be used. Can we say that T is expired? No, we cannot, because if we put 1 in this position, not 0 but 1, it means that A and expired T will result in expiration of the timer. But it contradicts the logic, because we're only interested in expired timer when none of the key is pressed. So that's why here it is 0. All right. So we have a bunch of combinations that are prohibited, and those combinations usually marked with star to denote don't care condition. So every combination of inputs that is prohibited results in the don't care condition at the output side. And those will be used for optimization purposes. All right. Now, let us see what can we do with this plot. Let me just check that my image was successfully saved. Let me try to find it somewhere here. So the file, okay, here it is. So I do have the image just in case, and let me so when I need the diagram, I can always switch to this. So that allows me to erase the diagram from this view, and I will now move on to implement my input encoder. So input encoder has 5 outputs, so the same procedure needs to be applied for all 5. And I will just do it once for illustration purposes. We're going to optimize our input encoder by means of drawing Carnot map that will have A, B here and CT here. and the combinations will be 0, 0, 0, 1, 1, 1, 1, 0. I remind you that you mark the Carnot map with respect to the gray code. 0, 0, 0, 1, 1, 1, 1, 0. Let us just do, okay, bit A or output A. Output A is activated on this position and on this position, which is AB 1, 0, right? 1, 0, 0, 0, 1, 0, 0, 0, and also 1, 0, 0, 1, 1, 0, 0, 1. So these two ones are marked on the Carnot map on these two cells. Now, let us mark all don't care bits, and don't care will be 0, 0, 1, 1. Then it will be 0, 1, 0, 1. And then 0, 1, 1, 0. And then 0, 1, 1, 1. And then 1, 0, 1, 0. 1, 0, 1, 1. And then pretty much everything starting with 1, 1. So okay. So now we want to optimize our logic function for A, and unfortunately these four don't care conditions don't help us to draw the cluster, but obviously the largest cluster that we can draw is this one. So, and this cluster will assume bit A to be unchanged, and that's it. Because bit B gets changed and both C and T get changed. So that is the optimized function for output A. It is just direct line. All right. Let me now show what will be, for example, with the N. And I'm going to do this in blue color. N is active with all zeros and 0, 0, 0, 1. Everywhere else N is not active, but we have a few don't care bits. 0, 0, 1, 1. That is don't care. And then 0, 1 everywhere but 0, 0. Okay, so don't care we have everywhere except the combination when C and T are 0, 0. And then we also have don't care set with 1, 0, 1, 0 and 1, 0, 1, 1. These two. And then we have the entire line with 1 1. Right? Now let us see how can we optimize this. Unfortunately, the B signal is not that good for optimization, because if we want a cluster to surround both of these, that is the largest cluster. It has to be either along one dimension or the other, but we cannot utilize any diagonal elements. And it has to be of the size 1, 2, 4, 8, 16. So that is the largest cluster we can form. So we can write B is equal to not A, not B. No, that's not B, that's N. Not A, not B. And if we want to combine these two, we see that C is not, but timer expiration could be anything. So not A, not B, not C. That is our N. Now you can continue with B, C, and T. So you will have an expression with B, an expression with C, an expression with T. And I just want to recall you that your input encoder has the 4 inputs and 5 outputs, A, B, C, and T. So those outputs, for example, A is just a straight line from A. N would be a bunch of inverters, so it will be a function from A, B, and C. And I don't know what will be B, C, and T, but the solution is pretty straightforward. So that is our input encoder. Let us do the state diagram. Not the state diagram, but something called excitation function. Excitation function is something that feeds our triggers. So I just want to recall the basics of a D trigger. So D trigger has input, output, and the clock signal. This is called D trigger. The clock signal is a periodic signal with the same period. Input can be any asynchronous signal. This is input. The output of the D trigger is value of input recorded at times when rising edge of the clock takes place. So in other words, we cannot say anything before the first clock signal, but then after the first clock signal it is defined, so this is out. It is defined at 0 because it was recorded as 0 here. And then it changed to 1 and remains at 1. And then again it got recorded at 1 and remains at 1. Then it was recorded as 0. Here it remains at zeros. One more. And then at 1. So usually we say that the output of a D trigger repeats the input shape of the D trigger, but the big difference is the length of pulses at the output are always multiples of time period of the clock signal. So for example, here this 0 is a single clock time, clock period. Here we have 2 clock periods, more than 1 clock period. Okay, that's how D-triggers work. And from the perspective of seeing that a D-trigger maintains the same level here, the same level here, 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 and here, we just say that a D-trigger is a logical element that contains some memory. It memorizes and stores the value, so it has the memory. If we want our D-trigger to memorize the state behind our finite state machine, we want to drive its input. As I mentioned before, we're gonna have 4 triggers because our finite state machine has 9 states. 9 states can be implemented in 4 triggers. The 4 triggers that we have will have 4 inputs and 4 outputs. And the way how our triggers, our D triggers, are fed from the input side is determined by the implementation of excitation function. Excitation function. The general idea behind excitation function is to say that we do have the 4 triggers, the 4 D triggers. Each one has data output. We do have input encoder that in our case has 5 outputs. Excitation function is a combinational logic that has 4 outputs which are connected to the data input of corresponding triggers. 1, 2, 3, 4, 5. And excitation function is also fed with the current state of the triggers. D0, D1, D2, D3. So in my case, D0 is the least significant bit, D3 is the most significant bit. Okay, what does it mean? And D1 and D2 are somewhere in the middle. What does it mean is that the 4 bits represented by triggers can be considered as forming a word, data word. That data word is being updated every time on every clock cycle. The clock cycle here is this. So when every clock cycle comes in, our excitation function produces 4 outputs. Those 4 outputs are getting fed into data inputs of triggers, and the outputs of excitation function depend not only of the inputs, but also depend on the current state of the trigger or the previous states of the trigger. In this case, excitation function has to be designed in such a way that based on the previous state and the input, we generate the new state that will be recorded to the triggers with the new rising edge of the clock signal. And that actually perfectly fits with the concept of our state change diagram. We do have a state and an input signal. So in other words, W will be the new state when the previous state was A and the signal N has been received. Okay? Now, from the perspective of excitation function implementation. We want to encode our states. So we do have, let me just list my states. My states are init, state A, okay, let me just, state A, state B, state C, A, B sequence, A, C sequence, A plus B, and W. A, B, C, A, B, A, C, A plus B, A plus C, and W. Okay, and we do have the D3, D2, D1, D0, D0. We do have the 4 bits in our data word. So pretty much we want to introduce combinations of those data bits that will be mapped to particular state. So if we don't want to go any further, we can just say these states will occupy the first 9 combinations, starting from 0 to 8. 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0. Okay, so these are our combinations. What about other possible combinations achievable with the 4 bits? Those will be used for don't care, because we're not going to allow our finite state machine to have the remaining 7 combinations. So the remaining 7 combinations that are possible with the 4-bit presentation will be mapped to don't care. Now, let us consider an example of the excitation function. So, to draw the excitation function, we have to draw it not just one, but one excitation function per each trigger. And let me just say that I want to draw the excitation function for example, trigger D0. I want to allow my triggers here, and then my inputs. My inputs are A, B, C, N, and T. These are my inputs. And the bold line will introduce the separation between the input side and output side. Okay, and I also want, let me change the color. My output will be D3, D2, D1, D0. I also want to allow all possible combinations of A, B, C, and T. And here is the tricky part. The input side of a truth table is supposed to list all possible combinations of binary numbers. How many combinations we do have? We have 4 bits from the triggers and 5 bits from the input encoder. Overall, we're talking about 9 bits. 2 raised to the power of 9 is 512, right? So our truth table will have 512 rows, and you are about to draw them all. But this is not the worst combination, not the worst thing. The worst thing here is that our truth function will contain 9 variables. 9 variables that have to be optimized, 9 inputs, better to say, that has to be optimized using Carnot map. So in other words, now we're dealing with 9 variable Carnot map. Previously we dealt with how many? 4 variable Carnot map. There exists a solution for the 5 variable Carnot map. So probably from this perspective, you want to say, okay, I'm not going to optimize this, because drawing 9 variable Carnot map, it's not an easy task. It is possible, and I really want you to discover a way, a solution for this problem from the perspective of using the same algorithm that is used to draw the Carnot map on optimized logical expression using Carnot map, with no respect to Carnot map dimension. So there are software solutions for that. You probably will not be able to find a calculator of the Carnot map online. Actually, they do exist, but usually they are limited with up to 5 or 6 variables. But if you're really interested in this topic, you may think of probably writing a program to optimize logical expression with 9 variables. Such solutions do exist, I can tell you. You will not likely be able to find them if you just search 9 variable Carnot map software in Google. But there are software packages, some of them are open source, that are generally used to design logical circuits. And Carnot map optimizers are usually built-in parts of those pieces of software. So you should be able to find them if you really search for them. But if you want a quick workaround, I would say you simply don't want to spend your time on optimization, because it will be hard without an additional help. Now, let me just illustrate the way it works. And obviously, I'm not going to draw 512 rows in my diagram here, but I want to demonstrate to you the idea. Let us say we know that based on our diagram, from the initialization state, we can go only to 3 possible states: to state A, or to state B, or to state C. In other words, there are only 3 outcomes of the initialization state. Okay? The 3 outcomes of the initialization state, that is the initialization state. Okay? The 3 possible outcomes are either 0 and all others like this, or 0, 1, 0, 0, 0, or 0, 0, 1, 0, 0. So I would say I'm talking about expansion of the first row. Okay? So these are the 3 rows where you want this data to be replicated. So in other words, now we're talking about 3 rows out of 512, where 0, 0, 0 combination will be repeated 3 times, and each of these 0, 0, 0, 0 combinations will be matched with one of these 3 rows. But we know that initialization state, if it is combined with signal A and no other signals applied, right? Then we change the state, and our new state from the initialization to stay with the signal A, it will be state A. State A, in our case, it is 0001. So, and that will be the new state. The old state, 0000, the input 10000, and the new state will be 0001, which is A. From init with A, we go to state A. From init with B, we go to state B, which is 0010. From init with C, we go to state C, which is 0011. Okay? Now, let us consider something more interesting. An example, for example, when we are in state W, we have state W here? Yes, we do. From state W, we have also three possible outcomes. Actually, it doesn't matter which state you are considering, but from state W, do I have any space? Yes, I probably do. From state W, we do have three outcomes. So in other words, that row I want to expand to three additional rows. And from state W, I do allow signals T, B, and C. Signal T will be 00001, 010000, 00100. So that is signal T, that is signal B, that is signal C. When in state W we receive signal T, timeout, we go to the initialization state. Right? 000, it is our initialization state. When we receive B, from W, we go to state A sequence B. A sequence B is 0100, 0100. When we receive C, we go to state A sequence C, 0101. Okay? And so on and so forth. So pretty much for every one of these states, you want to draw a group of rows that will correspond to number of outcomes from the particular state. And let me just estimate. From init, we have three outcomes, right? From, for example, A, we do have 1, 2, 3 outcomes. From state B, we have only 2 outcomes. From state C, we have 2 outcomes. From A plus B, we luckily have only 1 outcome. So let me just draw this. A plus B and A plus C, there is only 1 outcome. A plus B, and that outcome is signal N. And A plus C also signal N. And we go back to the initialization. Okay, so these 5 rows represent the real bottom part of the table. And clearly you don't want to draw all 512 rows, because majority of them will be populated either with zeros or with don't care. Okay. Now, let us see what can we do with don't cares. Don't cares, in our case, can be considered, can actually be achieved when, for example, in state init we receive timeout. So if in state init we receive a timeout, all our triggers become don't care. Okay. So this will help you to actually draw information on the Carnot map if you will decide to implement the 9-variable Carnot map. If you don't want to do this, just forget about don't cares and concentrate only on those roles that you in fact need. So I just want to remind you that state init has 3 outcomes. State A has 3 outcomes, B has 2, C has 2. These two have 1 outcome, that is 3 outcomes. A followed by B state has also a single outcome, same as A followed by C. And that is actually 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and they both go to 0. Okay, so 1, 1. We actually have a good chance to draw everything we need. So let me just draw the line to separate B and C. Actually, no, because I need to draw A, B, and C. And now I want to use the remaining space to draw 3 plus 2 plus 2, which is 7 rows. Okay, so that is for A, and there will be 1, 2, and 3. That is for B. And that is for C. Okay, so from state A we do have N, C, and B. N is pretty straightforward. C and B also pretty straightforward. Okay, so when N comes in after A, we go to state W. State W is 1, 0, 0, 0. 1, 0, 0, 0. When B comes after A, we go to AB, which is 0, 1, 0, 0, 0, 1, 0, 0. And when C comes in, we go to 0, 1, 0, 1, 0, 1, 0, 1. So I think now you see how this part can be created. Let me save this. And that is our excitation function. How would you implement it? That's pretty straightforward. Let us say we want to implement trigger D3. Trigger D3, you will have 4 additional rows here, and probably some of them will have 1, some of them will not have 1, but we don't see it right now. But D-trigger 3 has at least single 1. Let us assume that there will be all zeros here. It has 1 in this position. A single 1, a single row out of 512 that is marked with true logic. It means that you just want to write down the associated row, which is not D3, not D2, not D1, D0, not A, not B, not C, N, not T. And that will be a logical expression for D3. And then same can be done with D2, D1, and D0. All right. So that is your excitation function. And the last part that we need is the output function. The output function is easier. And the output function needs to have some references to how our outputs are assigned. Our outputs are assigned pretty straightforwardly. We want to allow a single output to those states that are marked with the asterisk. So in other words, we don't generate the output only for init and for W. And then we have 7 outputs for matching states and 1 extra output for the to actually start the timer. So the timer will be started when we are in state W. So pretty much the how many 7 plus 1 8 states or 8 outputs 8 outputs can be encoded with 3 bits. But that's actually, it depends how we implement the outputs. If we want the 8 outputs to be associated with 8 wires, with every wire to be connected to a single to a single LED indicator, then we want to allow 8 output bits. So we just draw 8 outputs. Okay, and let me just say that is my output 7, and this is my 6, 5, 4, 3, 2, 1, 0. Output 0. So it is capital O, it is not 0. And nothing here. So when we are in initialization state, we don't have any output. When we are in state A, there must be output that is associated with A. So let me just rename my output bits from all 7 and all the way to all 0, and let me just name them. That is my output A, B, C, AB, AC, and then A plus B, A plus C, and W, which is start of the timer. So clearly that output A has to be activated only in this position. Output B has to be activated only in this position. Output C only in this position. AB, AC, A plus B, A plus C, W. So the rest are just zeros. All right. Now, from the standpoint of implementation, we can just say that, for example, output A is a combination of the 4 outputs of the trigger, where D3 comes with inverse, D2 comes with inverse, D1 comes with inverse, D0 comes without inverse. That is the encoding for state A, and we want that output A gets engaged only if the finite state machine is in that state. So that will be function to be implemented in the output encoder for output A. Similar function we can introduce for B, for C, for D, and each one will have just a single bit, just a single term. That's it. Again, if you want to utilize don't care conditions, you actually can optimize every one of these outputs, because here we have only 9 rows, right? 9 rows with out of 16, which are possible with 4 bits, allow us 7 additional rows. Those 7 additional rows will introduce don't care condition for the output encoder. So don't care condition can be used to optimize A, to optimize B, C, etc., etc. That's pretty much it. So we went through the process of designing the finite state machine. So we started from straightforwardly listing our inputs, and then we eventually came up with the idea of careful state transition with certain inputs. And then we encoded our inputs, and then we introduced encoding for the states, and then input encoder, excitation function, output encoder. The only thing that we probably have missed is one optimization step that combines design of the excitation function with the design of the input encoder. You probably noticed that input encoder is a block that has 4 inputs and 5 outputs. Those 5 outputs go directly into the finite state machine. So if you combine the input encoder and the excitation function into the same design stage, then instead of 9 inputs, finite state machine would have 8 inputs. Okay? And another possible optimization here could be to consider the 9 states of the finite state machine. Right? We have 9 states. 9 states of the finite state machine require 4 triggers. What if we somehow redesign the behavior of this logic, and we'll find a way to reduce number of states to 8, not to be 9 anymore, but to be 8. 8 states on the finite state machine would require only 3 bits. So, in other words, excitation function, instead of having 8 input bits, would have 7 input bits. And 7 input bits sound very realistic to be implemented using Carnot maps. So these two optimization steps are possible, and if you really want to be involved in complex designs, of course, nobody is doing designs in this fashion anymore. People now use software and without even drawing finite state machines. You actually sometimes need to draw finite state machine to clearly understand how your automata works. But sometimes there are just easy tasks and nobody is doing this. This, what you experience right now, is the old school design approach that was in place probably with the first era of computers. This is how the first generations of Intel CPUs and other CPUs were designed back in 70s. This is the classic of computer organization. That's why we study this in this course. You want to understand how processor works. Processor is not just a magic unit that does something. It has been designed. It has been designed to respect the logic rules, etc., etc. I hope you were not so much exhausted by watching this video. That was meant to be a tutorial, interactive tutorial, but realizing the fact that you all have busy schedules, I recorded it, and pretty much if you watched up to this moment, you realize that it was recorded. So discussion is welcome. Make any questions on the discussion board. I will be more than happy to answer them. If no questions now, then we are done.
All right.
Did you get bored, exhausted, or both?
No, it wasn't so bad. It was pretty interesting, actually.
Good.
Alrighty, thank you.
All right, you're welcome. Have a good day.